Okay, depth first is it's slow in this situation because you have choices to make. Depth first is pretty fast for reverse Polish notation because you really only have one way to go, right? But when you start having choices and those choices can lead to a non-optimal direction, depth first starts to show its inadequacies. What's the word I'm looking for?
Weakness.
It's weakness, thank you. It's weakness. Depth first is more of a greedy algorithm because it just starts going one way and tries to and hopes for the best. All right. The other one's called, why is it called depth first? Because if you look at it, it's going depth. It's going to try to go up as much as it can, all the way as far as it can, and then start backing out. So if you look at it while it's progressing through the pictures, it's going piece by piece, or not piece by piece, it's going all the way in one direction and then pulling back. It's going through a depth. The other way to do it is called a breadth first search, where you basically start your position and you try going out where is everywhere you can go at step 2 or step 3 or step 4. And so you're searching out kind of a breadth way of looking at it. And we're going to go through that algorithm right now. And I called it breadth, so let's go ahead and make that function. Now, why does breadth has a D in it right here? I don't know, but it does. And let's not make things hard. Let's just copy and paste this validation stuff, including the whole visited thing. Actually, let's also copy the print maze. Perfect. Put it right here. That way we at least have it. But breadth first search is actually not recursive. We're going to get rid of that. We'll have it still call it. Just so we know that we're calling a different function. And let's go ahead and return 0. Let's go ahead and set up some more maze tests. So this is just straight up maze test. All right. I'll call it the maze test. Let's go test maze test to test breadth test. All right. So what's the shortest path here? Well, I think we talked about it last time. It was
18.
18. Perfect. And it's not can reach. It's, what was it? Shortest. All right. Go in the distance. 60. What?
2 down.
Oh. No, that's fine. I think it's talking about this. Yeah. Let's just comment that out. We don't need that. Good. Failed. Perfect. Excellent. All right. I could try and we could walk through and step through developing this algorithm. Fortunately, it's a little more complicated than that. But before we start, at least some intuition. What data structure is being used in depth first search? It is implicit. The maze is a 2D array. That's not what I'm asking. What data structure are we utilizing in order to support the depth first search?
Kind of like a stack?
It's a stack, yes.
Okay.
We're using the implicit stack of basically the C programming language, where every time you make a function call, you're adding to the stack, and then you pop from the stack. We could write this iteratively, where we used a stack class and just pushed and popped to and from it if we wanted to. Or we could write it recursively like this. Either way would actually work. I think the recursive way is easier to read, but this is using a stack. So, if the depth first uses a stack, what do you think the breadth first uses? Oh, right. It's a queue. But it's a queue of, queue of something. Well, it's a queue of where we are in the search. So we'll do std q, and I always forget the syntax for this. And I really hope the internet is working, because if I try and do this from memory, it's going to fail. Oh, good. All right, need the elevator music. Perfect. So we can push, pop, and we can ask for the back and the front. Perfect. All right. Q of, I'll call it points. And these are the items to visit. Okay, well, we haven't defined what a point is, so let's go do that. And I'm really not wanting to do getters and setters. I put it, all right, there we go. Okay.
Then call. Well, why not?
All right, so to visit. This is going to signify what we need to visit next. Well, if we want to visit something, we need to first put in the initial argument. So let's go, let's go and create a default constructor. There we go. To visit dot push point passing in sx, sy, and 0 because that's our initial distance. Okay, so we have a queue, and the queue is the initial point that we want to visit. Let me make sure that code compiles. It does not. Yes, classic. Put that semicolon there. Q is now a member of STD. Let's include it. Good. They compiled. All right. So, while to visit dot empty, and by dot empty, I really mean not empty. Screen's doing something weird. Point, I'll just call it P, equals to visit dot front, and then we'll do to visit dot pop. Remember, in C++ you have to do both. All right, let's go and make sure that at least doesn't go in an infinite loop. Good. So we're at point P. We have a point. What's the first thing we need to do? Well, similar to our recursive stuff, we need to validate the point. By the way, there's many different ways to set up this algorithm. I'm just trying to do it the way I believe is simplest to explain. So if p dot x equals ex and p dot y equals ey, then we want to return p dot distance, because that means that we have found, or we have arrived at the location. If p dot x is less than 0 or p dot x is greater than or equal to width, or p dot y is less than 0 or p dot y is greater than or equal to height, then we are actually not going to return, we're going to continue. Now, what continue does, and this can be somewhat confusing, is it's going to break from the rest of the loop and jump back up to the top. So it's going to finish end execution of this loop and jump back, or I'm sorry, end execution of the current iteration of the loop, sorry, and jump back up to the top and basically grab the next point. So this is equivalent to our returning or getting out of the recursive call. This is saying we have the right answer and we're just going to exit now. Okay, if we're at this point, then that means that we have validated point P, and we have also confirmed that it's not the end location. So the next thing we need to do is do maze sub, what was it, p dot x sub p dot y equals visited. And then now we want to add the up, down, left, right. So to visit dot push, and we're going to do what we got, point p dot x minus 1, p dot y, and p dot distance plus 1. All right. Anyone see an error yet? Let me go and print off what it's doing. That way we can see what's going on. So we're going to print right after we mark it visited. Oops. Ooh, no. And let's go and change to p dot x.
Also be careful since some of the brush first search stuff is in there as well.
I'm sorry, I couldn't understand you. Ooh, we just stopped. Well, that makes sense. Because if you try and go up, it's not going to happen. All right. So that's up. I think we went left last time, so let's continue with that. Minus 1. And then I believe we tried going down. Well, that's interesting. Let me finish this out before I forget. That way we have all 4 directions. Okay, good.
Why is distance only going up every once in a while?
Yep. Why is it? Oh, that's a good question. Okay. So we got a 2. So we're evaluating from 0, 0 to 9, 9, 1, 0 to 9, 9, 0, 1 to 9, 9. That's doing great so far. And then we're evaluating 0, 0 to 9, 9 with distance 2. What just happened? We went back. How do we not do that? V.
Yeah. Oh, yeah.
We'll continue. Then a wall. Yep. All right. Now let's run it. And it returned 18. Well, that was fast. Notice it checked every route, but it still told us the correct distance. Because it was checking each one by one. Let me show you the output of that. just to make sure it's clear what this algorithm is doing. So we're starting here, 0, 0 to 0. So really there's 2 points we can visit. 1, 0, which is distance of 1, and then 0, 1, which also has a distance of 1. And that's basically it, because notice right after that, it jumps to 2. Why? Well, if you check right here, the 2 things that are going to be added are 2, 1, or 2, 0, and 1, 1, both with a distance of 2. So if you check, we go 2, 0 first, and then we check 1, 1 next, both with a distance of 2. Now, we do check 0, 2 next, but that's because at this point you added 0, 2 to the list, and then you checked that as well. At that point, there are no other distances, other places of distance 2 to check. So we go down, now we're going to check all the ones with distance 3. We're starting down here because when we're at this location, we're going to go down and then we're going to go over. All right, now if you watch it, and I know it's kind of hard to see as I'm moving, but it's basically checking it from the bottom up, going along the diagonal effectively, is what's happening, at least in the open area. And then it's keeping track of the distance that it's traversed so far, so at the end it can tell you what the final distance is. FYI, the way this, yes, Google Maps does do something similar to this. This is you have the general idea of the algorithm now because it's breathing out. That is what it does. It actually has way more optimization than what we're doing by a long shot. But one thing I want to keep in mind, tell you, is that notice that since we're going each spot, we could keep track of where we have visited. Like we get to this point, then this point, then that point, then that point. That's how Google Maps works when it tells you the shortest route. So it can tell you go here, turn left. All those different turns are different points on the map. Now I haven't told you how the grid becomes a map. We will get to that at the very end of the semester because that data structure is very important, but it can be complicated. But that's the general idea behind Google Maps, at least at this stage. But notice that it's only going up with the distances, and I'm going to actually close this and jump over here and not print out the maze. And the reason for that is to make it so you can see that it's only incrementing on the distances. It never decrements. Basically, it's visiting them in sorted order in a way. But it's doing that by enforcement of how the algorithm works. Okay, let's go over to a couple more examples to make sure that this makes some sense. And I think we had test, let's do test walls. Whoops, actually, what should the distance be with test walls? Oh boy. I'm going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34. Sure. If we're wrong, I'm curious what the algorithm gives us. Hey, it passed. Well, that's good. Nice. Let's print off those mazes and dump it to out. I want to show you a couple things. All right, I jumped down to the end, and I'm going to go up a little. All right, so we're at this location. Basically, it's evaluated this and this or that are the 2 spots. So it can go either here or there. And I wanted to show you that it does actually check both. Notice it went left first, and then it tried going right. Now at this point, the distance of 33 is finished checking. It's going to check this left point, and then it's going to check the right point, and that's when it'll know when to stop because it's at the right point. Now it does check the left point first, which is great, and then it says pass because once we get to it, it's going to jump over there and give us 34. So if I had a really complicated maze, it's not that it's going left and right from the bottom. I just wanted to show you that in the open maze. But in this one, it's actually branching out the different steps one by one. And if it was a really large maze, like what you may get from your auto grader, then it, if you were to print it out, you would see it kind of spread out from different points. Okay, and there is one very important test, that we need to make sure we pass, and that's the blocked test. And let's go ahead and, where are we? Swing for the fence. Oh, we failed. Oh, actually, what did we return down here? We returned 0. Well, that'd be why. Let's try turning -1. Okay, great. So if it's blocked, it can't go anywhere, we're out. All right. So here's the breadth first version. Any comments on this one?
Are there any situations where a depth search version is better than the breadth?
So first off, anytime, okay, oh, hold on, let me back up. What do we implement our stacks with? We could use a linked list, but if you're using the computer stack, it's an array, right? What's the queue probably going to be implemented with? A linked list. I'll tell you now, it's kind of a hybrid because it actually makes sense to make a lot of blocks and then use it. But anyways, so pushing and popping from an array is always going to be, and that O of 1 is always faster than a linked list O of 1. So that operation is faster on a depth first. And if you don't really have decisions, like with the reverse Polish notation, then the depth first is definitely faster. But in this case, the breadth first is going to win. To really answer your question, it does depend. Because remember you were saying earlier, if you set it up to where you took the correct route to begin with, depth first is going to get to the answer way faster than breadth. And if you look up what an A-star algorithm does, it tries to do kind of a hybrid where it like shoots out and tries to find a closer spot and then do like a mini breadth first search in there. So there are times when depth first is faster than breadth first. But right now it really does appear like breadth first is winning. That's just not always the case. So there, it depends. Great question. Another one?
I think I have heard of A-star before.
You've heard of A-star?
I think so.
Yeah, that algorithm came out when I was in undergrad. Yeah. We'll get to graphs, actual graphs, and then it's a lot more fun. Fortunately, it's at the end of the course, but whatever. Any other comments on this one? Usually, it's better to understand the algorithm so you can whip it out. This one, it may make more sense to just memorize it real quick because it's not too complicated. But this pops up a lot, all the time, especially when you get to graphs. So memorizing this, set the queue up, give it an initial point. While it's not empty, go have at it, try and find all the stuff and validate things, and just keep going. That's going to be done a lot. All right. Any more questions before we go to your lab? We're only going to be like 5 minutes late. Perfect.